Hello and welcome to another lecture of Introduction to Astrophysical Fluids. As promised earlier, in this lecture we will discuss more in detail the subject of instability and linear wave modes in fluid media. Okay, so it is true that the subject has already been introduced in this course in the context of the sound waves. Now we know that sound wave is the way of response of a compressible fluid medium to a weak external perturbation or disturbances in order to repair the disturbance. Now, if the disturbance is not weak enough, then we actually showed that there can be nonlinear effects and development of discontinuity, shocks, this type of thing. Okay, and but that was very much, case specific. Now in this part and also in next week's lectures, you will see that we will try to address different type of problems related to such waves and instabilities. Okay, but for this week we will start with a very interesting but very simple case. It is called the case of convective instability. But before even starting discussing about convective instability, I would like to make a formal introduction to this waves and instability in case of a fluid. So if you recall our previous discussion, you can easily see that a polytropic fluid generally responds to a very weak perturbation, we call a first order perturbation, in terms of sound wave or acoustic mode. And in this discussion, we will investigate the question of stability and instability of a fluid in more detail. It's a general perspective. Okay, so for that, let's go back to the particle picture in Newtonian mechanics. Let's say a particle which is resting, staying at rest on the top of a mountain or in a valley. Okay, in both the cases, the total force of on the particle is zero and the particle is at rest. But really, do the two cases correspond to the same type of mechanical state? Well, both of them are equilibrium conditions. That's true, because the total force is vanishing. Now the question is, the mechanical equilibrium is there. Now the question is whether same type of equilibrium are they corresponding to? Well, the answer is no. Here this is corresponding to unstable equilibrium. Here this is corresponding to stable equilibrium. You all know. Because a weak perturbation with respect to this configuration would just lead to a linear oscillation, simple harmonic oscillation. Okay, and finally with time it will try and finally it will recover its original configuration. However, for this type of case, this if you perturb the particle a bit very weakly, this particle will go farther. Or if you perturb like this particle will go farther, okay, from its original configuration or original position. So this is the concept of stable and unstable equilibrium. Whether the particle after a weak perturbation would try to fight against the perturbation or would try to support the perturbation. That distinguishes the stable equilibrium versus the instable equilibrium case. Now in case of fluids, okay, we cannot really distinguish this type of position type of thing, but we can distinguish several type of steady state. So in case of fluids, we do not search mechanical equilibrium position in general, rather we search whether a steady flow is stable against external perturbations or not. Of course, the external perturbations must be weak, otherwise we cannot do linear analytical theory out of it. Okay. Now in case of steady configuration, so for a fluid we will say it's a steady configuration or unsteady, It's a configuration. Okay, so then I mean, if the configuration is non-steady, then there is no question of searching whether we can perturb it, and we search for unstable equilibrium or stable equilibrium. But if the fluid is steady, that means the fluid variables are no longer explicitly depending on time. In that case, okay, the fluid is stable only when any weak or first order perturbation is repaired by the fluid using linear wave modes, as exactly we saw in the case of acoustic wave or sound waves. Okay, but the growth rate of the first order perturbations, okay, in this case are only given by linear differential equations. And what is the advantage for that? So if we have a weak perturbation with respect to a stable a steady configuration, then we first call that configuration as steady, stable and steady. Okay, then the second thing is that we can express the growth equation or the evolution of the perturbation as linear differential equations. If you remember, that is the method of linearizations, which we already discussed or introduced in the context of sound waves. Okay, that means for example, the non-linear advective term vanishes. Okay, and what happens under this case, that each perturbation can be thought as linear superposition of Fourier modes, each of which can then be treated individually. So that is the property of a linear differential equation. So in general you can say that every perturbation can be expressed as a superposition of various plane waves type of thing, sines and cosines. Okay, and then once this is done, finally, if you remember, finally we find out the dispersion relation relating the frequency and the wave vector for each mode. Okay, and then also we all discuss whether the fluid, the wave is dispersive or not, this type of thing. Okay, now, but it is true that in the case of sound wave, we just directly showed that there is a wave mode. Okay, now in case of steady configuration, in case the steady configuration is unstable, then what happens? Then this perturbation is no longer repaired by the fluid medium. Then it grows in time. The system supports to aggravate the perturbation, degree of perturbation. Then linear theory fails. However, linear theory can still be useful to indicate the onset of the instability and also the behavior of the instability at its initial phase, and that is the theory of linear instability that we will do also in next lectures. Okay, now it is true that most of the practical cases of fluid flow, it is observed that a steady state is neither absolutely stable or absolutely unstable. A steady state can be stable or unstable depending on the value of one or more specific quantities of the fluid. Okay, so a steady state can a steady configuration of a fluid. If I just ask you that, for example, is a steady configuration of such fluid is stable or unstable, the answer is, well, it depends on the values of different quantities of the fluid. Okay, and depending on one or more specific quantities of the fluid, that is the relevant quantities for the stability of the fluid, okay, it may change. The nature of the steady state can change from stable to unstable, from unstable to stable. Okay, if, for example, we consider a liquid at rest in a container and the container is heated from below by some energy agent, like a burner, the fluid remains stable up to a certain value of temperature gradient. That means the temperature is, the heat is transported from one layer to the other layer just by conduction. So macroscopic motions cannot be visualized. However, beyond a critical value of the temperature gradient, okay, the fluid is unstable. The fluid becomes unstable to global convective motions, and you can actually see that in this vessel, there will be a convective flow type like this. Okay. So what is a convective flow? Convective flow means a vertically up and down flow. So the fluid down, the downward fluid which is getting heated, it is getting lighter, so it flows up, and the fluid which is which is on the upper side, this is less heated because the heat energy source is at the bottom, okay, for this type of system, okay, and then this is heavier, so it comes to fill the blank part or the empty part in the downward level, okay. And in this way, when this heated fluid goes up, and it becomes actually again, it loses its temperature, okay, and finally it becomes again heavier and comes down, okay. And this is a cyclic process, and maybe you know that one of the primary source or origin of rainfalls in the equatorial region is the convective rainfall by the convective motions, okay. It's called convective rainfalls, okay. So now this convective motion basically designates the transition from the stable steady state to the unstable steady state, okay. So that means that if your system is now, if your system is perturbed with respect to a state where the temperature, the heat was conducted just by conduction, microscopic method, then any small perturbation would have been died out because of some linear modes or something, okay. But if it is not, then the system is actually globally convective in nature, and any perturbation can be aggravated, okay. Now the transition from a stable configuration to an unstable one is mathematically called a bifurcation. Although we will not be discussing bifurcation in details, but that is just for your interest, okay. Once again, when the system is unstable and the perturbation grows, how to say, the perturbation grows beyond a critical value, then it is no longer possible to treat them linearly. Then the nonlinear theory must be taken into account, and the analytical scope is also very much limited. And you know that a system where the total, the entire nonlinear motion is established is called a turbulent motion, okay. So this is a system of utter interest for many researchers, including me, okay. So but whenever we are talking about instability, we are talking about linear instability. That means this is the initial phase of an instability. Now it is true that people always think, and that is the correct way, of course, that whenever there is a fluid system is unstable, or it conceives some linear instability, then the fluid with time, and when the disturbance grows with time, then it how to say, it has a transition from normal motion to the turbulent motion, okay. So from linear instability with time, it is possible to go to turbulent motion. That is the phenomenological view, which looks quite evident. However, it is very interesting to note that till today there is no very formal and systematic theory to show that a linear instability can really lead to a turbulence just by using a very systematic bifurcation type of rules, okay. So these are very mathematical details, okay. Now coming to our point, here in the scope of this discussion, we will be only talking about the investigation of linear waves or linear instability, okay. and then we will actually investigate them using regular process of linearization. But even before doing that, let us do something which is much more simpler and interesting for astrophysics. Here in this course, I am doing something which are much more interesting for astrophysics. Okay. So what we will do, basically we will show by a very hand waving method that we can approximately find the criteria of the convective instability of a fluid medium, which was initially at rest, of course. Okay. So now let us suppose an ideal gas in hydrostatic equilibrium. So it is totally at rest, so trivially steady. Okay, in a uniform gravitational field. Okay, so in this case we are no longer neglecting, we can no longer neglect the body force because the system is in hydrostatic equilibrium, and you know that the hydrostatic equilibrium is established by the interplay between the pressure gradient force and the body force most of the cases. Okay, so of course viscosity is there, but viscosity is actually unimportant, non-important for this case. Okay, now the gravity acts vertically downwards for our case. This is, we are just now defining the system. Okay, so gravity is acting downward, so here you can see this one, and z is taken upward vertically. Okay, so gravity will be acting on along minus z direction. Now the system is in hydrostatic equilibrium, that is our assumption. So one can simply expect, if you remember our discussion of hydrostatic equilibrium, okay, one can simply expect that both the pressure and density, they decrease with z, and actually you can see a stratification. Okay, so it's a layered type of stratified fluid. Okay, where p and z, p and rho both are decreasing as a function of z, and we try to perturb that system. How? We take a small blob of gas, okay, and after taking, we quickly displaced, the quickly is very important, quickly displace it vertically from a layer which was, from a layer below to a layer above. So the layer below had the density and pressure P and, pressure and density respectively P and rho, and from this the blob is now displaced to a level where the surrounding pressure and density, they are given by P prime and rho prime. Now remember, before perturbing, this was, everything is in equilibrium, so for a given layer, and I am actually taking the mass of the blob of the fluid, which was an indistinguishable entity from the surroundings before taking it. Okay, so both the blob and the surrounding had pressure and density P and rho. After displacing this one, okay, vertically upward, okay, so now the blob just has reached to a layer which was not its known layer or familiar layer. So this layer had a pressure and density P prime and rho prime, and because this mass is adiabatically displaced, so this mass will also have some adiabatic change, and due to that change, thermodynamic change, okay, due to that change, the pressure inside of this blob is now, so this blob is foreign entity in this layer. Okay, this blob will have a pressure which we can call as P star and rho star. Here I have written P prime, I will explain this. But as a result of the sudden displacement of the blob, it will have a different pressure and density P star and rho star with respect to those of the surroundings. Okay, so the blob is no longer indistinguishable with respect to the surroundings because the surrounding is a new one. Okay, now since the system is undergoing an since the system was quickly displaced, and that's why we are actually talking of adiabatic displacement. Okay, then we can actually think that the if you just consider the initial configuration of the initial thermodynamic state of the blob and the final thermodynamic state of the blob, we can simply write this equation that P by rho to the power gamma is a constant. So P by rho to the power gamma is equal to P star by rho star to the power gamma. Okay. Now coming to a very important point. It is reasonable to assume for our case that the blob pressure gets equilibrated very quickly after the blob reaches to the new ambience. So after it reaches to the new ambience, finally it's the walls are not adiabatic in nature. The walls are not rigid in nature. So mechanical equilibrium will be very quickly established. And actually, you know maybe that the mechanical equilibrium for fluids are much fast established than the thermal equilibrium. Okay, but so P star can almost be equal to P prime. Okay. However, rho star and rho prime, they are significant. They are not equal. Okay, they are different. Okay, so now in this equation we can now write, can simply replace P star by P prime, and then we can write this equation as rho star by rho prime will be equal to rho star by rho will be equal to P prime by P whole to the power 1 by gamma. Okay. Now once again, here we are talking about adiabatic case. So gamma is not a general polytropic index, but this is exactly equal to the Cp by Cv, or 1 plus 2 by F, where F is the degrees of freedom of the system molecules. The system constituents. Okay. So now we concentrate on the surrounding. That was the story for the blob. Now what happens for the surroundings? For the surroundings, so we can say that starting from this level, one can actually go vertically upward and reaches to another pressure P prime. If we suppose that we have displaced the blob by a very small amount, then P prime can be written as a Taylor expansion just up to the first order. So it will be P plus dP dz times delta z. So delta z is the amount of displacement vertically. Okay, so dP dz is the pressure gradient, normal pressure gradient in the normal fluid. So for our case, for the surroundings. Okay. Now, so P prime by P will be 1 plus 1 by P dP dz times delta z. Okay. Now P prime by P, this is equal to this one, and this one raised to the power 1 by gamma will give you rho star by rho. And that exactly what we will do now. So rho star by rho will be equal to P prime by P whole to the power 1 by gamma. Now we can say that this is nothing but 1 plus 1 by P dP by dz times delta z, and just remembering that this can be assumed to be moderate, where this can be very small. So this total factor can be assumed to be sufficiently small with respect to 1, and so this raised to the power 1 by gamma will simply help us expanding these things like a Taylor series. And again, it's not like a Taylor series, sorry, like we can expand like a binomial series type of thing. And finally you will have rho star will be equal to rho plus rho by gamma P dP dz delta z, because this is nothing but 1 plus this is equal to 1 plus 1 by gamma P dP dz delta z. Okay, and now you just multiply throughout by rho. Okay, and then you have this equation small a. Okay, again, from the decrease of density in the stratified fluid, so that was the story for the decrease of pressure, and then we have just mixed this with the the relation of the densities for the blob. Okay, now coming to the law of decrease of density in the stratified fluid, and for the surrounding of the new position, we can say that rho prime is equal to rho plus d rho dz delta z. Okay. Again, the same thing, because delta z is small enough, so this is the this is the gradient of density in the surrounding gas. So we can write the new density with respect to the initial, new layer density with respect to the old layer density plus this term. Okay. Finally, we assume that the gas is ideal. So from kinetic theory, we can simply write P is equal to N kBT. N is the number density, T is the temperature, and this is Boltzmann constant. So P is equal to, we can write rho kBT by m, where m is the mass of one particle. Then for 1 mole of gas or fluid, we can write rho RT by m. Okay, and this m is constant, this r is constant, so m is the molecular mass actually, or molecular weight of the constituent particles. We are taking 1 mole for our convenience. So P will be equal to some constant times r, constant times rho times T. So then you just take log and differentiate both sides. You will have this type of relation. This is a very handy relation. Okay, this type of technique. So you take a log and then you get rid of, or log and then differentiate, so you get rid of all the constants. Okay, and finally you can write that you can actually do this ddz of the whole, these things. So roughly saying, you can divide the everything by dz. Okay, so that sometimes we say, but this is not the correct way of saying. Okay, so if you do that, you will see that d rho dz is equal to rho by p dp dz minus rho by t dt dz. Okay, now combining, so that was equation number C. So combining, so first we will subtract b from a, and then we actually replace this value of d rho dz in this subtracted result, and finally we have rho star minus rho prime is equal to minus 1 minus 1 by gamma rho by p dp dz plus rho by t dt dz. Okay, now you remember that, now try to understand one simple thing, that okay, one thing is that for an ideal gas and in a hydrostatic equilibrium, in general dp dz and dt dz, they are negative. Combining all these things, finally what we get is the difference between the density of the blob in its new position minus the density of the surroundings of the new position. Okay, it makes sense. Now at this point we can think of stability only when the density of the blob is much larger, not much larger, but it's larger than the density of the surroundings. That means the surrounding will consider this one as heavier with respect to this their layer, and that's why the this blob will try to come back downward. But if rho star is less than rho prime, that means this rho, the blob's density is less than the surroundings density, then the blob will find itself lighter in its new position, and then it will be simply dominated by the buoyant force, which will help it go further, go vertically upward further. So we started by displacing it to vertically upward direction, and if rho star is greater than rho prime, this direction, this motion is actually counterbalanced by its downwards motion. So this gives us the condition of stability. Whereas if rho star is less than rho prime, then the vertical direction then the displacement in the upward vertical direction will be supported somehow, and it will go upward farther and farther. Okay, so that simply says that the system is stable against convective motion, okay, if rho star is greater than rho. Okay, of course, when the particle is displaced a bit vertically upward and it continues going upward and upward, then the system will actually be becoming convective, right? But if the system is just displaced infinitesimally and it comes back, then the system is convectively unstable, convectively stable. Okay, and that is the condition where rho star should be greater than rho. Okay. So for stability, we actually need the whole thing to be greater than 0. Now, since dp dz and dt dz, they are negative, that means that this thing should be greater than this thing. And that's exactly, I mean, the mode of this thing should be greater than the mode of this thing. Okay, and that's exactly which we have written over here. Okay, that is the 1 minus 1 by gamma times 1 by p dp dz mod should be greater than 1 by t mod of dt ds, and that is the condition of stability against convective motion for a system which was ideal gas type of thing, but it was at hydrostatic equilibrium initially. Okay, and this condition is known as famous Schwarzschild stability criterion. Okay, now you see that basically this is a interplay between the dp dz and dt dz. When dp dz overshoots dt dz, then we have stability. When dt dz overshoots dp dz, then we have instability. So that's what I said, that if the temperature gradient is greater than this value, this is the critical value of the temperature gradient for which the system just can retain its stability. But beyond this, 1 minus 1 by gamma t by p dp dz, the system is unstable against convection. Okay. So you see an important temperature gradient. That's what, now coming back to our initial example of heating of container of fluid or liquid from below. So when the temperature gradient is gradient exceeds this critical value, then the system is unstable. Okay. Although our system is very much, analysis is very much simplified, we have not really parted systematically the equations of dynamics. But at the end, our method is very much giving some conclusion which is quite intuitive. And believe me, this type of method actually is used to check systematically if some parts in the interior of a star, for example sun, are subject to convective instability or not. This type of simplified treatment. Of course, simplified in which sense? That is, the system is ideal gas. The system's mechanical equilibrium will be very well established, but not the thermal equilibrium. This type of things are a bit rough, although reasonable. Okay, but you can do something much more systematic, but then also the conclusion will be the same. Okay, there are several books which contains this type, the systematic approach of this problem, for this to address this problem. Okay, now, but finally the good news is that the Schwarzschild stability criterion is remains the same even with this systematic and much more rigorous treatment. Now we simply write the equation, okay, of motion for the fluid inside the blob. So we would like to see what happens for the for the dynamics or for the blob. Okay, so of course you can see that for the blob we can approximately write rho star. So when the blob is displaced already, then after being displaced, the force density equation for the blob is nothing but rho star d2 delta z dt2. So that is its acceleration, instantaneous acceleration, will be equal to minus rho star minus rho prime g. So that is the effective gravity field which is acting on the blob. Okay, and if you simply just replace this value of this rho star minus rho prime, you can simply see that the equation is looks like this: d2 delta z dt2 plus g by t dt dz minus 1 by gamma times t by p dp dz times delta z, and that is equal to 0. Okay, so now this one is some quantity which looks like square of a frequency. Okay, and you see that is another point we can make here, that if we have this type of equation, then we will just check that whether this one is positive or not. If this one is positive, then this is the square of frequency. Okay, and if this one is negative, then this is not a square of in real frequency. Then the instability comes into play, that we will check. But here you will see that this quantity can be positive, that you have to think further and just tell me, I mean, what I would like to make here, that this quantity is positive only when this Schwarzschild stability criterion is satisfied. That means they are equivalent. Okay, this is easy to see. Okay, so if this is now positive, then this is nothing but the square of a frequency, and we will see that this is nothing but the frequency of the wave. Okay, so this is nothing but the frequency of not even wave, sorry, this is the frequency of the oscillation. Okay, so and you can actually check that this is known as Brund-Weisela frequency. Okay, and of course, when this type of frequency, so what does that correspond? This corresponds to the coming back of the mass blob to its original position when this is displaced vertically upward initially. Okay, and it actually leads to linear wave modes. Okay, it actually leads to in linear wave modes that you can see. So for the particle, you can see this is an oscillation type of thing, but the whole fluid medium, so here we have just written for the mass blob, but for the whole fluid medium, if you do the correct linearization, and then you can actually see that you can have linear wave mode with the same type of frequency, which is root over this thing. Okay, and that wave is known as internal gravity wave. So remember, internal gravity wave somehow says that your system is thermally stable, or your system is convectively stable. Okay, with respect to some temperature gradient. Of course, if the temperature gradient is more and more enhanced, then your system can switch from a stable system to the unstable system. Okay, so that was a very simplistic treatment with convective instability. In the next discussion, we will try to, so that will be in the next week, of course, we will try to enter in the formal processes, and we will discuss of many other type of instabilities and possible wave modes and instabilities. Okay, because at the end we have to remember that most of the cases, the astrophysical phenomena, they are associated with different type of wave modes and instabilities. Okay, thank you very much.